So good evening everybody. This is Fiat Lux 3. And why do I call this Fiat Lux 3? Well, let's remind ourselves that Fiat Lux means, well, that if you want it in Hebrew, or that if you prefer Greek, but most of us would prefer Let There Be Light. Fiat Lux was originally a trilogy in which I described in the first installment the nature of light. This was a series of demonstrations in which I demonstrated a measurement of the speed of light, a measurement of the wavelength of light, looking at the colours of light and looking at polarisation. In the second element of Fiat Lux 2, I looked at how the nature of light influences the working of lenses and mirrors and hence the design of telescopes. So it doesn't matter if you haven't seen either of those two talks, they are recorded if you want to go and watch them later. But the idea is, having established what light is and how it can be used to make telescopes, the third element of the Fiat Lux trilogy is this talk this evening, which is looking at the Large Synoptic Survey Telescope. In other words, looking at an example of how our understanding of light has allowed us to make telescopes, and this particular telescope, which is coming online very soon, will allow us to make more discoveries about the universe. Because of my liking for Star Wars, I decided to subtitle each of these talks, and Fiat Lux 3 has been subtitled, because it's the Large Synoptic Survey Telescope, I've subtitled it Episode 3, the LSST Jedi. So let's have a look at the contents. First, we'll look at sky surveys. Why do we survey the sky, and what existing surveys have already taken place? And then the Large Synoptic Survey Telescope, why do we need yet another survey? And if we do need another survey, why do we need a special telescope to carry it out rather than an existing telescope? What science do we hope to get out of the LSST? And what technology do we need to actually deliver on that science? And I'll finish with looking at the survey strategy for how the sky is going to be surveyed and what's going to happen with all the data. So we can ask the question, what's out there? That's a pretty fundamental question that we're all interested in. And you might say, well, don't all telescopes try to answer that question? And the answer is, well, no, not really. Most research telescopes, when you think about it, look in detail at objects we already know about, objects that have already been observed and catalogued and classified. That's, for instance, what Hubble spends most of its time doing. But if we want to know about what's out there, we need to survey the entire sky, not simply look at the things we already know about. And surveys of everything in the sky, down to a certain limiting magnitude, have already been carried out. For instance, if we go back far enough, we go back to the Palomar Observatory sky surveys. Back in the late 40s, early 50s, they were carried out using the 48-inch Schmidt camera on Mount Palomar, where thousands of photographic plates were taken. This was followed up in the 80s and 90s by a second survey of the whole sky, carried out with more sensitive plates, and these plates were sensitive to blue or red light, so a very limited amount of colour information. Again, thousands of plates taken to cover the entire sky covered once by the entire survey. If we come to this millennium, we then go digital, the Sloan Digital Sky Survey, which has taken quite a few years in the early part of this millennium, where the photographic plates have been replaced by CCD cameras, and not so much thousands, but more like 1 million images have been taken with a couple of 2-meter class telescopes. That overlapped with Pan-STARRS towards the latter part of the Digital Sky Survey from Sloan. Pan-STARRS stands for Panoramic Survey Telescope and Rapid Response System. As you probably know, that's been responsible for catching various nova, supernova and comets that have been coming round. And beyond Pan-STARRS, we have the Large Synoptic Survey Telescope. It has since been renamed, but I'll continue with that name for the time being, the LSST. You see the dates there are nominally this year for another 10 years of the survey. Actually, the schedule has been nudged back a little bit because of COVID, so perhaps it'll become operational or at least start to take first light, perhaps 2023, something like that. So why do we need another sky survey? We can think about how many objects are visible in a survey as a function of time. What sort of number are we hoping for? Well, to give us a yardstick, remember that that grey line represents 100 billion, and that's roughly speaking the number of stars in the Milky Way galaxy. It, coincidentally, is roughly speaking the number of galaxies in the observable universe. Maybe a little bit more than that, but 100 billion gives us a sort of reference as to what we would like to catalogue. If we start with Palomar, we find that in the 1990s we were cataloguing something like 100 million objects. When we move over to the digital survey of Sloan in this millennium, that's bumped it up by a factor of 10 or so. And when we go to Pan-STARRS, we're now looking at billions of objects. But what we're trying to do is to get as close to that grey line as possible, as close to that ceiling of cataloguing essentially everything in the universe. Well, we're not going to get there. Even everything in the observable universe is quite a long shot. But LSST will get us close. So you can see that in its 10-year program, the LSST will get us close to that hundreds of billions of objects ceiling. And of course, it's been in preparation for quite some time. It might be operational, let's say, in a year or two. So currently, we're roughly where that red arrow is. And we're still keeping our fingers crossed that COVID won't interrupt its operation any further than it already has. Why can't an existing telescope be used? Why do we need a new telescope to do a new survey? Can't we just use one of the hundreds of telescopes around the world that exist already? Well, if you want to survey the survey the sky, the telescope and the camera, so you could argue the combination of the two, the telescope-camera combination, must have a number of basic characteristics. It must have a wide field of view, otherwise it'll take you forever to survey the entire sky. It must have a fast set of optics to keep the exposures short. And it must be able to go deep, in other words, to be able to see faint objects. If we can only catalogue the bright objects, then we have no chance of cataloguing a large fraction of the objects that are in the observable universe. So it needs to be wide angle, it needs to be fast optics, and it needs to be capable of going deep. You can do a little bit of horse trading between these three characteristics, but for a telescope to excel as a survey telescope, it really needs to be good in each of these aspects, wide and fast and deep. So just a little bit of an aside to make sure we're all on the same page. What do we mean by fast in the case of optics? The word is often used when describing either camera lenses or telescopes, and it's quantified by the ratio of the focal length of the imaging system to the diameter of the lens or the mirror that is collecting the light. The F number is the focal length divided by the diameter. And a lens or a mirror or an optical system with a low F number, in other words a large diameter for a given focal length, that produces a brighter image. And when you're dealing with cameras and taking pictures of objects, for instance in daylight, if you have a bright image, that means you can have a faster shutter speed, in other words a shorter exposure. And because the shutter speed was faster, in photography, in camera language, we talk about a set of optics being fast if you can keep the shutter speed fast. So fast optics means a relatively large diameter for a given focal length. So let's just have a think about slow and fast optics in the context of a hypothetical image we want to take that might, for instance, require an exposure of 1 minute if we had optics with an F number of 2. If the F number goes to f2.8, that means that the image is only half as bright, which means we have to expose for twice as long to get the same image, to collect the same number of photons, in other words. And you can see as the F number goes up and up and up, in other words, as the focal length gets long compared to the aperture, or if you like, if the aperture gets small compared to the focal length, then the exposure needs to get larger and larger and larger. For any of you who carry out some astrophotography, you know that generally speaking, you try and pick a lens with a nice fast F number. In other words, a small F number that gives you a large aperture for a given focal length. So if you're doing astrophotography and you're taking pictures of large chunks of sky, you might choose f numbers of f2 or f2.8 or f4 or something like that. We can ask ourselves what are the f numbers of some telescopes we know about. For instance, the Hubble Space Telescope has got a mirror diameter of 2.4 meters, and its focal length is nominally 57 meters. And if you divide 57 by 2.4, you find that the f number of the Hubble Space Telescope is closer to f22 than any other number on that scale. So it is not fast in the optical sense. It's got a very small mirror compared to its focal length. So what about, you say, something with a larger mirror? What about the European Extremely Large Telescope, which will be coming online again, hopefully in only a few years' time? It's got an absolutely huge 40-meter diameter mirror. So surely that's fast. Well, not in the sense that even though it's 40 meters diameter, the focal length could be anything up to 750 meters. And if you divide 750 by 40, you find that the f number of the Extremely Large Telescope is somewhere close to f16. So you can see that optically, the sort of telescopes that we've got either on the ground or currently in space are not optically fast. If we want a good survey telescope, we really need something much faster, optically speaking, than f22 or f16. And we'll see what the f number of the LSST is shortly. So we want wide angle, we want fast, and we want deep. If we have a simple camera with a wide-angle lens, well, we can certainly cover large chunks of sky, but we can't go very deep, and we can't usually get very fast optics. If we have a camera with a telephoto lens, then we can certainly go deep. I've used a DSLR and a telephoto lens, for instance, to image a quasar that is some 12 billion light years away, receding from us at twice the speed of light. It is possible for a DSLR and a telephoto lens to go relatively deep. But of course, we don't get a particularly wide angle, and neither are particularly optically fast. And we've just seen that the Hubble Space Telescope and the Extremely Large Telescope can definitely go deep. They can definitely see very faint objects as long as they expose for a long time. Remember, the Hubble Deep Field was something like a 10-day exposure. So they're not wide angle and they're not fast. And so we need a dedicated survey telescope like the LSST that ticks all the boxes of wide angle and optically fast, and still deep enough to give us very faint objects. Hence the mantra of the LSST is wide, fast, deep. This gives you an idea of what it looks like. It's a huge mirror, 8 meters in diameter, and it covers a very wide angle thanks to the large camera, which we'll look at shortly. And it should be capable of imaging down to something like 25th magnitude, or 26th magnitude, or 27th magnitude, depending on the object it's looking at. One of the key aspects of the whole LST project is that the entire sky that it can see from its base will be imaged every 3 nights. Remember, the Palomar survey took more than a decade and covered the sky once. This will cover the sky that can be seen on any given night in no more than about 3 nights. In other words, it can cover a third of the night sky each night. And that means every patch of sky will be imaged more than once during the 10-year lifetime of the survey. In some cases, hundreds of times. In other cases, perhaps thousands of times will a particular chunk of sky be revisited by the survey. That means if anything changes, either changes in position or changes in brightness or changes in colour, we don't simply get one data point for each object, which is all we got from, for instance, the Palomar survey, where you just got the brightness of one star and the position of one star at one time. In this case, because the survey will be over and over and over again during its 10-year lifetime, we will not simply have the position and colour and brightness of a given object like a star or a galaxy. We'll see how that changes as a function of time over the 10-year time period. And it's that aspect that makes this survey so different from all previous surveys. It's not only the number of objects that it will catalogue, tens of billions of objects. It's the fact that it will survey them over a period of time. What's the science, or at least what are we hoping the science that we'll get out of this survey? Well, we'll be able to look at objects within the solar system, and it will be surveying stars within the Milky Way galaxy, and it will be looking at many billions of galaxies throughout the universe. To do this, we'll need some novel telescope optics, basically the largest digital camera ever built, and when the data starts flowing, it'll push data processing capabilities absolutely to the limit. It will generate the largest catalogue by far of objects that are out there, and hopefully that will then underpin many strands of scientific research, probably for decades to come. So let's just very briefly touch on the principal scientific aims of the LSST project. On the local scale, we'll be looking at objects within the solar system. Effectively, it will take an inventory of what's out there. In doing so, it will clarify the formation of our solar system and help us understand how other solar systems came to be. When we look on a larger scale at the Milky Way, we'll be able to determine the structure and evolution of the Milky Way and find the properties of stars in the Sun's neighbourhood. It probably, on the whole, won't give us the same precision as Gaia. Remember, Gaia is looking at the positions and proper motions of stars in the Milky Way, but it will cover a great deal in terms of numbers. Beyond the Milky Way, we'll be looking at galaxies, and it's hoped to catalogue somewhere in the vicinity of 20 billion galaxies. The positions, the size and the shape, if they're close enough, and if relevant, the colour. And through looking at galaxy collisions and the star formation processes in galaxies, we'll get better understanding of how stars form and better understanding of how galaxies evolve, because it's galaxy collisions and mergers that dictate how galaxies evolve over billions of years. If we think about dark matter, gravitational lensing will be used because it's possible to image billions of galaxies, some of which will be in the foreground and some of which will be in the background. There will be lots of opportunities for looking at gravitational lensing, and that will allow us to get better data about how dark matter is distributed throughout the universe. And by looking at how dark matter is distributed at different distances, remember different distances means different look-back times, so we're getting effectively a history of dark matter, that will tell us about dark energy, because that will determine the distribution of dark matter as a function of time. And that hopefully will give us a better idea of what this mysterious dark energy is that seems to be tearing the universe apart and accelerating the expansion of the universe. In addition, it will be possible to pick up lots of supernovae. The idea that dark energy is making the universe expansion accelerate, that is based on the observation of dozens of supernovae. But it's hoped that the LSST will be able to pick up hundreds, if not thousands of supernovae every night, and every night of its 10-year programme. So dozens of supernovae has given us the idea of dark energy, but by the time the LSST has done its job, we will have data on thousands, if not millions, of supernovae. In a single exposure of the telescope, which will be nominally 15 seconds, in a single exposure, it's expected that there will be 5,000 moving objects in the frame. Now, over the 10-year survey, it's expected that many millions of asteroids and trans-Neptunian objects in the Kuiper Belt and thousands upon thousands of near-Earth objects will be found. Some of them, of course, we already know about. The larger ones we've already caught by other surveys. Perhaps 10% of them we already know about, but we've got 90% of the others that we really need to keep an eye on as well. Some of them are potentially hazardous. We know about some of these objects that are circulating and crossing the orbit of the Earth. And we know that in the past, large objects have been rather disruptive to life on Earth. We're not expecting anything that big to come around again, but even small ones can be highly disruptive, and we really need to keep an eye on all the objects that are potentially going to hit the Earth. If we think about the solar system, we know the terrestrial planets make up the inner part, and if we move out, we get to the gas giants and the ice giants, and if we move out further, we get to the trans-Neptunian objects, some of which are in extremely eccentric orbits, which make us think that Planet 9 is out there somewhere and is predicted to exist, but we're not quite sure where. But if the LSST is going to survey essentially the entire sky, then if Planet 9 is out there, then it will be found. In other words, there's almost no way that a planet with the mass that's necessary to cause the orbits that we see in these trans-Neptunian objects, there's almost no way that this object can hide from the gaze of LSST. And once LSST finds it, then other telescopes will be trained on it for more detail. What about the Milky Way? Well, it was only relatively recently that it was established that the Milky Way has 4 spiral arms. That's simply because it's very difficult to see what sort of galaxy we are in, because we're looking at it from the inside. If only we could leave the galaxy and look back at it, we'd get a much better idea of how it's constructed. We think now that the Milky Way is a barred spiral with 4 spiral arms, and we're sitting down here near the bottom on the Orion spur. Excuse me. But a single exposure of the LSST, in other words, a single exposure covering the sky, will survey a volume of the Milky Way some 10 times larger than all previous surveys. Remember that most surveys will only give you the brightest objects, which means in the case of the Milky Way, the stars that are closest to us. But the survey volume will increase by a factor of 10 after only a few nights of surveying the sky. And by the time the entire survey is complete after 10 years, it's expected that the volume that has been surveyed will be something like 1,000 times larger than all previous surveys put together. A spin-off, not one of the main reasons for the LSST, but a spin-off is, if you're observing billions of stars over and over again, you're probably going to catch a few new exoplanets as well. So we know that the Kepler satellite has been dedicated to finding exoplanets by staring at a particular patch of sky. But the LSST is going to be surveying effectively all the sky it can see from its site, and it's quite possible that it's going to pick up lots of new exoplanets. Some of them might be in stars that are in the Magellanic Clouds, and that might be the first observation of an exoplanet in another galaxy. Perhaps you've heard that there's been some evidence, some tentative evidence for an exoplanet in another galaxy, but that's based on the idea that, well, if it was really a transiting exoplanet, we won't actually know that for another 30 years or so. That was an X-ray source. So it looks like the LSST could be the first telescope to actually find an exoplanet in another galaxy. If we come to galaxies themselves, we know that galaxy interactions are quite common. Hubble, of course, has looked at lots of galaxies, including individual isolated galaxies, as well as galaxy interactions and galaxy collisions. And they've turned out to be much more common than we first thought, and are indeed responsible for most of the galaxy evolution that we think we understand. So images like this clearly show a couple of galaxies in collision. But if we look at this galaxy, we might say, well, this is M63, that looks like an isolated galaxy, I can't see any other galaxies there. But if we take that image, just remove the colour, invert it for clarity, and just play with the contrast, we realise that there are in fact huge loops of gas around this galaxy which indicate that this one has been tidally disrupted, probably by a close approach of another galaxy in the past, or possibly a merger with a smaller galaxy, producing these large tidal tails. And these are quite common. Again, if we take this image and invert it for clarity, we find that this galaxy, again, has got a huge tidal disruption, presumably from an earlier interaction. And indeed, we think the Milky Way galaxy has such a loop extending around the Milky Way itself. So understanding these will help us understand the formation of our own Milky Way, as well as the formation of many other galaxies that exist. What about the dark side of the universe? Everything that we can see in terms of visible light is only about 5% of the universe. In other words, ordinary matter, hydrogen, helium, all the stars, all the galaxies that we see seem to be only 5% of the universe. 27% of the universe is dark matter. We know it's out there based on its gravitational pull, but we don't know exactly what it is or exactly where it is. 68% of the universe is the even more mysterious dark energy. That's thought to be responsible for the acceleration of the expansion of the universe, and eventually, presumably, it will rip the universe apart, unless for some reason the amount of dark energy in the universe changes in the future. And we don't have a clue what that is or why it's there. If this so-called dark sector accounts for 95% of the universe, we really ought to try and understand a little more about it. So we know dark matter is there based on the behaviour of galaxies in galaxy clusters and the behaviour of stars in galaxies, the way galaxies rotate. And our understanding based on gravitational lensing tells us there's far more matter out there than can be explained by just the luminous matter of all of the stars and all of the gas and all of the dust. So we think there's a whole dark web of dark matter out there. But it's rather tricky to measure, it's rather tricky to observe because you can't observe it directly. You have to look at its influence on other aspects of things you can observe. So we don't know, for instance, whether dark matter is uniformly spread throughout a galaxy or whether it's patchy, as this little artist's impression might indicate. But it's hoped to do gravitational lensing that I mentioned earlier. Some galaxies will be in front of other galaxies in the distance, and the amount of matter in the foreground galaxy or galaxy cluster will distort the more distant galaxy images in a way that depends on how much dark matter is present. The top left image shows you what you might expect in a simulation if there isn't much dark matter, and the bottom right simulation shows what you might see if there was more dark matter present. The distortions are more dramatic. And so by looking at not just a handful of galaxies, but by looking at millions, if not billions of galaxies, it might be possible to build up a map of how the dark matter is distributed throughout the universe. And on a slightly larger scale, we can look at the dark matter web. Here the dark matter is represented in red, but of course we can't actually see that. But what we can see are individual galaxies which are influenced by where the dark matter is. And again, looking at a handful of galaxies doesn't help you. But if you look statistically at millions or billions of galaxies, you can see small deviations in the arrangement, in the positions or the orientation of galaxies based on the small tug, the gravitational pull from dark matter which exists throughout the dark matter web throughout the universe. So by observing lots of galaxies and looking at their positions and orientations, it can be inferred where the dark matter web is and how it is distributed. And that will help us get a handle on dark matter, and because we can do this at different times, that will give us a handle on dark energy. Okay, those are some of the science highlights that we hope to get out. But how is that going to be delivered by this telescope? It's going to need a unique optical design. It's going to need the world's largest CCD detector in a camera. And it's going to need, of course, an outstanding observatory site. So where are you going to put this telescope? Well, the best sites on the world map there, Hawaii in the Pacific, a volcanic island. Another set of volcanic islands are the Canaries, La Palma and Tenerife in the Atlantic Ocean. And of course we have Chile, the Atacama Desert. So these three red dots there represent the three best sites in the world. And the site that was chosen for the LSST was the Atacama Desert, the site in Chile. So that's where it is. The little marker there shows you, Cerro Pachon. I think I've got the pronunciation right. If we have a look at it, no, that's not it on the right-hand side there. This is the view from the mountain on which the LSST is being built. That's the view of another telescope. That is Gemini South. Remember, there were two Gemini telescopes, Gemini North, Gemini South. That is Gemini South on the neighbouring mountain, as it were. And so the mountain that we are sitting on to take this picture, the top of the mountain was blown off, and then you need a dozen or so people to walk around it saying, I don't like the look of this, or whatever. And they decided that, yep, that was fine, so they started building. And the telescope, that's probably a little bit old now, but that was the state of the telescope a little while ago before COVID interrupted some of the construction. That gives you an idea of what it will be like when it's complete. There's a little telescope off to the side that will be monitoring the condition of the sky. What's going on inside that observatory building? Well, the telescope will be in the turret on the left, and then there will be laboratories for removing the mirror and re-illuminizing it every once in a while. The optical design is very interesting. If you want to cover a wide field, 3 degrees of sky, and you want it to be aberration free, there's no point in having a wide angle if it's distorted towards the edges. So if you want to have a 3-degree field of view that is essentially aberration free, they went with a novel 3-mirror design. The primary mirror is about as big as you can make a single mirror, 8.4 meters in diameter, and the focal length is about 10 meters. Remember, the focal length of Hubble is more than 50 meters. The focal length of the EELT is something like 750 meters. So with a mirror diameter of 8 and a focal length of 10, the effective focal ratio is about f1. It's about f1.2. And remember that astrophotographers are usually delighted to have a lens with something like f2 or f2.8. So f1 is really fast. This is the optical design with all of the mechanics of the telescope removed. Let's just dim that out a little bit. So light hits the primary mirror and then is reflected to a secondary mirror and then comes down to a third mirror. Notice that the third mirror is actually the same piece of glass as the primary mirror. In other words, the primary mirror is made to one shape around the edges and to a different shape in the centre. So that piece of glass acts as the primary mirror and the third mirror. Having hit the third mirror, it then goes into the camera. This is how the primary and tertiary mirror were made. You put lots of glass blocks into a furnace, and to avoid having to grind too much of the surface away, the furnace was spun to produce something close to a parabolic shape, and that means that you then have less material to grind away when you want to figure the actual mirror. So you put all the glass in, close up the furnace, and then spin the furnace. Melt the glass and then slowly cool the glass down. A camera that was looking inside the furnace shows you what happens to the glass just at the point at which it melts. And this video is shown 3 times. There's the glass melting and then sinking into the ribs between the hexagons. And again, melts and then sinks into the honeycomb. One more time, it melts and then sinks into the honeycomb. The honeycomb is there to give you a ribbed structure on the back of the mirror, which makes it a lighter mirror for a given size. That's what the mirror looks like when it comes out of the furnace. That's what an 8.4 meter mirror looks like before they started grinding the mirror 1, mirror 3 shapes in this particular blank. So not only is it important that you get the optics right, but if you want a 3-degree field of view, you clearly need a large detector. There's no point in having a huge field of view if your detector is really small. So the camera required the world's largest CCD detector. And no, that's not it. This is just to give you an idea of scale. That's roughly speaking the size of the camera in your mobile phone, probably. And you can see how large it is compared to a fingertip there. By comparison to that scale, the chip inside the Hubble Space Telescope is a 16 megapixel chip of that size. In other words, it's this big. If you look at the camera, that's how large it actually is. 4 by 4 centimeters, about 16 megapixels. A little bit bigger probably than the camera you have in your SLR camera. If we take that as a yardstick, 16 megapixels in a chip 4 centimeters in size, let's take that 16 megapixels and let's add 8 identical CCDs around it into a package. So now we have 9 chips, each of which is the size of the Hubble chip in camera number 3. Let's take that package and let's add a few more packages. That package, let's add another 8 of those. And then let's add another 12 of those. And then let's add a few CCDs for focusing and tracking. That is the size of the detector that's used in the LSST. It has lots of individual CCDs for imaging, it has a few for tracking and guiding, and it has a few to double check focus. The whole array is 0.6 by 0.6 meters, and the entire number of pixels generated in the image is 3 billion pixels, 3 gigapixels, which are read out in 2 seconds. And for those of you who are struggling to work out what 0.6 by 0.6 actually means, that gives you an idea of how big the detector actually is. It is almost the size of a coffee table and almost too big for this camera to actually see in one go. So that's a one-to-one mock-up of how big the detector actually is. And of course, with a detector that large, 3 billion pixels per image, per exposure, in 15 seconds it can take an exposure and then spit out an image which is 3 billion pixels. There's no way I can show you what that would look like, because of course the monitor that I'm using on this computer is only a megapixel or 2, and the monitor that you're looking at might be a few megapixels if you've got a high definition monitor in front of you, but there's no way we could possibly display a 3 gigapixel image. So just to give you a very rough idea of what we might be expecting, let's not attempt to show the whole image. Let me just show you what we would expect to get in that little black square there. If we simulate what we would expect to get in a 15-second exposure of sky just within that little black square, we might expect to catch something like that. Quite a few thousand stars, probably many hundreds if not thousands of galaxies. And that's what you would expect in that megapixel, and remember the full image that you get is 3,000 times the area of what you're currently looking at on the screen. And that's what you can catch in 15 seconds. So you can imagine how much you could catch in 15 seconds, how much you could catch in a few hours of imaging. To give you a rough idea of the scale in terms of sky, there's the moon, about half a degree of sky, and there's a reminder that the Hubble Space Telescope has a very small field of view. Yes, it's got its 16 megapixel sensor, but it can only look at a tiny fraction of sky. If you wanted to survey the entire sky with the Hubble Space Telescope, I think it's been calculated that it would take a few hundred years to do it. So yes, it's wonderful that the Hubble has been working for decades, but the Hubble is not a survey telescope. On this scale, if we wanted to show the field of view of the LSST, well, we can't fit it into this image. The best we can do is to give you an indication of the edge of the LSST field of view. 3 degrees of sky, more than 3 degrees of sky. It has filters on board, filters that go in front of the sensor, and as you can see here it goes from 300 to something like 1100 nanometers, so we've got the visible part of the spectrum from 400 to 700, and in addition we've got a little way into the UV and a few infrared filters as well. So it covers the same sort of range as Hubble. Mainly visible, a little bit of UV, and the Hubble goes into the infrared as well, which is why we've been able to get infrared images to compare with what we would expect from the James Webb Telescope in due course. That gives you an idea of what it looks like. You can see that the camera itself is quite large. You've got a decapitated man on the right there for scale. And you can see individual filters, you can see just how huge they are. They have to be more than 0.6 meters in diameter because they will cover the entire CCD chip. You don't want different filters for different parts of the chip because then you wouldn't be able to compare pixels to pixels. What is it going to be covering in terms of sky? This gives you a whole sky map. In other words, we're looking at the whole sky unwrapped so that we have here everything from the North Pole to the South Pole with the equator running down the middle. The colour scale here indicates how many times a particular patch of sky is expected to be visited during the 10-year lifetime of the LSST. And you can see that most of the southern sky is going to be visited many hundreds of times, perhaps 700, 800, 900 times. Any particular part of the sky that's of particular interest to a group of researchers might be visited more than 1,000 times during the 10-year project. In addition to looking at most of the southern sky, you see that from Chile you can't see particularly far north, but they will cover the Milky Way as far as they can go, and they will deliberately cover the ecliptic in the northern part of the sky, simply to cover the whole ecliptic to try and catch as many solar system objects as possible. There'll always be a few missing in very eccentric orbits, but they hope to catch most of the solar system objects by covering all of the ecliptic. You see that the south celestial pole is not going to be visited as often as many other parts of the sky. That's simply because the south celestial pole is quite low in the sky, as seen from Chile, and there's no point in looking at objects that are very low in terms of their altitude. So there's no point in spending a lot of time looking at objects very close to the south celestial pole, with the possible exception of the Magellanic Clouds themselves. What about the data that's going to be coming out of this? I've said that the camera is very high resolution, 3 billion pixels per image, and the images will be coming off once every 15 seconds or so. So how might you store the data? The LSST is going to generate shed loads of data. So how are you going to store it all? Well, let's just remind ourselves of how disk storage has gone over the years. Anybody remember these things? Yeah, floppy disks. A floppy disk can hold 1 million bytes of information, roughly speaking, barely enough for a single digital image. So if I go on Safari and I take a picture of zebra, well, that might end up as something like this, a 2 megapixel image, and it might occupy half a megabyte of disk, for instance. So with a floppy disk, I could store a couple of images. If instead we went to something like this, a DVD, which can store many gigabytes of information, a gigabyte of course being 1,000 megabytes, so that would be enough to store many thousands of photos. I could go on Safari, and even if I took lots of pictures all day, every day, I could probably fit all of them onto 1 or 2 DVDs. So for personal use, a DVD is a great way of storing thousands of images. But how quickly would the LSST fill up the data if we were restricted to only using DVDs? Well, for me, that many DVDs would last me much more than a lifetime. I think probably 10 lifetimes, and I wouldn't store that many images if I went on Safari every year. But the LSST would fill all of those DVDs in about 30 minutes of imaging. So we have to go to something larger. We have to go to something like a terabyte disk. A terabyte is 1,000 gigabytes, so effectively a terabyte disk is the equivalent of something like 200 DVDs, or something like a million floppy disks. So if we use terabyte disks, where would we be at? Well, if we had this many terabyte disks, something like 20, that would just about be enough for one night's observations. Something of order 15 to 20 terabytes of disk space would be needed each and every night. The number of clear nights should be at least 300 and something clear nights every year, and the project lasts for 10 years. Add in some calibration data, some darks and some flats and some other data, and you're probably looking at something like 500,000 terabytes of data by the time the project has finished. Now, admittedly, as time goes on, terabyte disks are going to get cheaper and cheaper. And who knows what storage we will have available to us in 10 years' time. But for the moment, that means that we've got to put a lot of disks aside for storing all of this data. How are we going to get the data? Well, every 30 seconds or so, the LSST will take 2 images. 15-second exposure, another 15-second exposure. That means about 15 gigabytes of data when you work out how much data is required to store each pixel of information. It takes 2 images, it always takes them in pairs, such that, for instance, it can tell if a cosmic ray happens to have gone through the sensor and produced a bogus hot pixel in an image. A simple comparison tells you if they're identical or if they're different. So every 30 seconds it will generate 15 gigabytes of data. That will be sent via a 100 gigabit per second intranet, which would take about a second or so. That would take it from the mountain top down to the headquarters at the base of the mountain, at La Serena. They will hold a local copy and then they will send a copy to the supercomputer clusters in North America. So in about 4 seconds, those 15 gigabytes will be sent from South America to North America over a couple of internet links. Fiber optic, of course. You may ask yourself, how on earth do you get 40 gigabits per second out of your fiber optic? And the answer is that's easy for fiber optic. It can actually take more than that in principle. So if you ask yourself, why are you not getting 40 gigabits per second out of your internet? Well, that's because you have to fight with everything else that's going down the fiber as well as your data. And remember, the internet is absolutely chock full of YouTube videos of cats and other things as well. I believe some YouTube videos don't involve cats. I've not actually found any, but there we go. If you could somehow put a YouTube cat filter on your data transmission, then you find your data goes from A to B much faster. And they are confident, having done some tests, that they can get 15 gigabytes of information from South America to North America in just a few seconds. Where does it actually go to? It goes to the NCSA, the National Center for Supercomputer Applications, at Urbana-Champaign in the USA. There they have a whole set of supercomputers which are going to crunch on this data as it comes in. Each set of data, each image that comes in is going to be crunched and compared to previous nights or previous weeks or previous months' data. And what they intend is that they will be able to tell nominally within 1 minute, they will be able to tell how many things have changed since that patch of sky was last imaged. And it's anticipated that there will be 10 million events per night. An event means something has changed. An object has moved. An object has changed its brightness. An object has changed its colour. 10 million events every night. And the intention is that scientists will be able to sign up for being told when an event of interest to them has happened. Maybe scientist A is interested in supernova and wants to know if a supernova has gone off in particular types of galaxy. There might be hundreds or thousands of those every night. Scientist B might be interested in the appearance of an asteroid that we didn't know about. Scientist C might be interested in a star suddenly getting brighter, perhaps a nova starting to brighten. I don't suggest you sign up for all of these events, otherwise your phone will be pinging with 10 million texts every night telling you that something interesting has happened. In addition to setting up these so-called events of interesting things have happened, we want other telescopes to go and have a closer look at them. In addition, it will be slowly, image by image, night by night, year by year, building up a catalogue of as many objects as it can see. And it's anticipated that that catalogue will be something of order 20 billion galaxies and 17 billion stars. Based on the limiting magnitudes that they think they can achieve, that's what they think they're going to be able to catalogue. It's obviously only an estimate because who knows what's actually out there. So that's an amazing feat of data capture, data transmission and data number crunching. And it will of course be necessary to have automatic algorithms sifting through this data looking for interesting things. There will probably be some citizen science as well, but you can't rely on individuals sitting down and analysing hundreds of thousands of terabytes of data over the next few years. It will certainly keep a lot of PhD students quite happy, but there needs to be automated analysis as well. So it will be possible at some point to get an app which tells you what the LSST is doing. For instance, it will tell you what it observed last night, how many supernovae it's found last night, how many supernovae it's found in total to date, how many million has it found in the last few years. What does a particular patch of sky look like as seen by the LSST? You won't download entire 3 gigabyte or 3 gigapixel images. You'll be able to download a patch of sky as seen by the LSST once it's started to build up a picture of the whole sky. So the LSST is quite definitely on the horizon, literally and figuratively. I'm not sure quite how behind schedule they are. 2022 was nominally the start date as of a couple of years ago, and I know that COVID has given it a little bit of a hit. Once they get first light, they'll have some calibration to do, and then they will start the survey proper. Just an addendum before I finish. I've been talking about the LSST, the Large Synoptic Survey Telescope. But just to confuse things, in 2019 the observatory was renamed, and it was renamed the Vera C. Rubin Observatory in recognition of the contributions that Vera Rubin made in measuring the influence of dark matter on galaxy rotation back in the 1960s. LSST has been an acronym that's been used for the last 10 or 15 years by all the people in the planning of the design and the construction and the testing of the LSST. So they were rather reluctant to let LSST go as an acronym. So the observatory has been called the Vera C. Rubin. It was decided that the telescope itself would be renamed the Simonyi Survey Telescope to acknowledge the money provided by some private donors. So the LSST no longer refers to the telescope, that's now the Simonyi Survey Telescope. But to preserve the LSST, they've decided to describe the project of surveying the sky. They're calling that the Legacy Survey of Space and Time. Ta-ra, we've got the LSST acronym back again. So lsst.org still is valid. They didn't have to change the domain name because they can now use LSST to refer to the survey rather than refer to the telescope itself. So I've told you about why we survey the sky and what had already been done prior to the LSST. And I've told you why we need something like the LSST to survey billions of objects that will then feed into research and more detailed analysis by other telescopes like perhaps the James Webb, perhaps the Hubble, perhaps the EELT and other ground-based telescopes. I gave you a little taste of some of the science that the LSST will be able to deliver on. And I've told you about the technology that will allow that to happen. And then I finished giving you a taste of how the survey is going to be done and how much data is going to be generated. Exciting times ahead. Thank you all for listening.